fight through our technical difficulties while our esteemed president starts our meeting.
We're having trouble getting that jerking up to our.
Yeah, we've got several of them, but technical support is on the job.
That's the problem before, but the problem is the way around it. It's hard.
Well, Jim, I can get this started while these guys are doing it. So these guys here in Cranbrook are you guys know you see the Zoom session. All right, hi there. Welcome to this meeting of the Warren Astronomical Society. And once again, we're having technical support issues, but we're working through them. Everything is rebooting. Yeah. Okay, so are there any first timers here? We have no first timers here. Bart Alex. Okay, if you haven't renewed your membership, you can via PayPal on our website or pay this man here during the break. If you're interested in going to a GLAC meeting, GLAC hosts Astronomy at the Beach. If you like,
I'm not getting any sound.
They meet on the second Thursday of the month. We would like to see more WASP representation there at GLAC meetings. This April is Global Astronomy Month, where everyone's encouraged to promote astronomy any way they can, just like we do here. So keep doing that. Statewide Astronomy Night has been moved from April 29th to what, Jeff? This Saturday. So Statewide Astronomy Night has been moved from May 29th to this Saturday. So if you're planning on going there, that is at the Belle Isle Nature Center. So, our first event at the Metro Parks was canceled because of the Michigan Nebula, and I was all set and ready to go to it too. I had everything all set. We have Metro Parks is having a family camping event on June 10th at Hudson Mills Metro Park. If you've never been there, it's west of Ann Arbor, kind of a distance. Very nice park. My wife and I went out there. The event is just going to be like a campfire event. They're expecting 150 people, and they just want somebody to set up scopes and do a sky tour. So this one's going to be super simple. Hard enough. More technical difficulties. Okay, Marty Coos has agreed to house our library of old astronomy books. We just need to get that to him. So I'm going to be sending an email to Jonathan and Diane and Marty and organizing how we're going to move all that stuff from its current location to its new location. Is anybody interested in getting some WASP swag like Jonathan? He's got it. For the people in the audience, we have coats with a WASP logo, and we also, I don't have a WASP mug, and I'd like to see it. And I know the Vatican Observatory Foundation uses a print-on-demand service to put our logo on certain things like shirts and stuff. If you're interested in getting one of these guys or some WASP logoed swag, get with me at the break. And we'll talk about possibly setting up a Zazzle account and getting some of those things done. So, all right. Those at the podium will be able to see our esteemed guests online. Our esteemed guests online, you'll be able to hear us when we talk through here. And I'm not sure if that's, well, that may help, that may not. We're trying to duplicate. See there, it's there. Some things just disconnected in between, so the display does not work. So
I just put it out, duplicate, there it is. And it didn't come out yet.
Yeah, so I saw that change, which means it recognized that there's a signal, goes through the floor, and there's no voltage.
So David Levy, can you please speak? I said, are we
Yeah, can you hear me?
our audience here?
Can you hear me? I'm speaking with you now.
Don't hear David.
Can you hear me?
Let's say something again, David. I think
I can hear you.
You can?
Yes, but I'm not in the
Okay,
meeting.
let me do my poem
I'm not in
then.
the meeting. I'm on line two.
Say, Dale Teamy, can you speak? Make sure we can hear something.
Yeah, I can say
We are
something.
not hearing anything here.
Okay, nothing's coming through. Okay.
this is both great ideas. So start with your laptop because it's a quicker one. Let's leave this connected, Bob, so we don't lose our crowd. You're connected to our WebEx. Connect to the WebEx first, grab your projector, although I don't know if there's any way other than to, yeah, and project. Grab a projector.
All right, so Dale, can you try to talk again?
Okay, can you hear me now?
No, I can hear you through the speaker here, through the laptop.
So,
I can hear you.
Just the laptop, eh?
All right, try again.
Okay, can you hear me now?
we can hear you.
Where's the speaker here? Can I?
It's right there. And it tries to reduce the feedback. Yeah, I wouldn't flash it.
All right.
I also do a system check, make sure my slides work. Can anyone hear me?
Yes, I can hear you.
Thank you.
Problem is, we all hear each other on the WebEx and on YouTube, but they're not hearing us in the auditorium,
Okay,
which is where they need to hear us.
I understand.
Yep.
I can no longer hear anybody.
muted here.
All right, yeah, you are next, Adrian.
I can hear you.
All right, good. All right, it's time for the treasurer slash what is the Astronomical League report. And while I'm giving this report, there will be people looking to connect things here and there. This is the HDMI cable. This is this cable. If you want to use it, I have to extend. Right. So after we will, but we won't do it right now. We're going to give this report and then we're going to do some moving. So my report is that the Treasury report is in the WASP. Many thanks to Dale Timmy, Mark Gedzier, and those of you that helped me keep the Treasury in line. And for the Astronomical League, the Astronomical League will have its national, I want to say national conference in Baton Rouge. Our own esteemed Dr. David Levy will be giving one of the presentations along with David Eicher, Fred Espenak, and Fred Espenak will be talking in Baton Rouge in July for the Astronomical League. If you are an Astronomical League member, you can go to this conference. So Astronomical League dues are $750 on top of your membership dues. If you've already paid, you will become a member for July of up till July of 2024. The Astronomical League's year is kind of halfway between the calendar year. And so that's Astronomical League, Treasury reports in the WASP. And let's move on to our next report.
I have a feeling I know what Mark Kezier is going to say about our secretary report. It's in the WASP. He had nothing to say before. Okay. Outreach, Kevin.
It's pretty much been covered. Just again, the Belle Isle thing this Saturday, 7 to 10.
For some reason, the sound is not working on this.
You guys got to mute just a little. The WAS
Mute.
had two presentations, one at the Ann Arbor Library and one at the Detroit Public Library. On the 20th of May, there'll be a scout group coming out to Stargate. And one other thing about Baton Rouge, if you go to the Astronomical League in Baton Rouge, one of the best astronomical facilities you'll ever see is the LIGO Observatory. It's the gravity observatory, gravity wave observatory. It's right outside of Baton Rouge. They got a great museum.
I can't hear
there
them
you
at
can go
all.
see. And that's it. You know, we can hear you though, so probably best
WebEx.
to mute your phone.
WebEx.
Lawrence. That would be great. Okay, thank you.
Okay. Special interest groups. Marty. Marty? Who is gone? Oh, okay. So I don't know what's going on with the sun. I haven't actually seen the sun. Let's go. Actually, we had a big aurora recently, and that's actually not true. As I've been saying many times, my phone keeps telling me we've had solar flares. So when we have one here, two of them this morning. There we go. 10 hours ago, an M7.12 solar flare this morning. So again, my phone vibrating off the Marty, the sun. Do you want to talk about the sun? Here, Marty Booth, we'll talk about the sun. The sun's still staying pretty moderately active. There's been a large sunspot group on the sun for the past 2 weeks. It's finally rotating away. The whole group is larger than Jupiter, but not that many components to it. There's two semi-large parts to it. There's a small cluster of the sunspot cluster right in the middle of the sun in the northern hemisphere. A little bit active in other regions like H alpha, but not very active in white light. And there's a new group just starting to rotate onto the sun right now. So keep an eye out for that one. Maybe that one will start to be a bit more active. So still a lot of activity on the sun. Thank you, Marty. We don't have David. I'm waiting that we're getting a projector up here so we can get you. Sorry. So, let's see. Continuing on. All right. Wait on that. All right. So, do we have any astronomy questions from the audience for our members? No astronomy questions. All right. Well, what time is it? It is. We usually take a break about now. So why don't we take a break about now? We'll reconvene at 8:20 and we're going to do some IT stuff here in the meantime. David, if we get this up and running, I'll have you do your thing as soon as we get this projector working.
What I'm looking forward to it. So we're gonna figure it out, David. Don't you worry. All right, let's give you this.
All right, so reconvene at 8:20, maybe a little earlier for David.
Okay, right.
This is the break. All right, this is good news. I got a projector.
Come on and work, you. Fucking.
Got the connection. Take USB and it's right there.
I'll take that cord.
That's this cord. It's connected.
Oh, it is. It's right in there. All right.
Okay, here we go. Go to HDMI 1 and okay.
Enter.
Enter.
He's connected. He will share his screen.
Okay, that works. All right. Let's get someone who hasn't gone to the bathroom to talk, and let's see if it where the sound comes out. Yeah. Go ahead and say something
me?
in your tablet. Oh, I can hear you just fine
Okay.
through the computer.
Yeah.
Yeah,
Okay.
you do. There may not be a speaker on the projector.
No, it does have it.
Try Epson.
It was an Epson. Epson.
Okay. Are you still connected to the? You want to get in? Yeah, go ahead and get in.
And just
Yeah, I've seen this.
speaker like this. So
Did you?
it's a speaker. Okay. Can someone please try talking? Testing.
All right.
Can
Yes.
you hear me?
Yeah, we can hear you.
Yeah,
I
we can hear you.
Yeah.
You hear me now?
Yeah, we can hear you from the computer.
Good.
Now we need the big old.
What? Yes, I'm talking right now. Can you hear me okay? And there? Good. You want me to sing?
Sure.
I wouldn't anyway. I wouldn't. I'm gonna go mute again, okay? How you doing, David? How you doing, David?
Oh, I'm doing fine. I hope you guys can hear me.
Nice to see you, pal.
Good to see you all too. And I'm doing okay.
Did you see the pictures from Espinac?
No, I have not seen them yet.
You got to see those pictures from Espinac. They're amazing. I'll tell you what, I'll send them to you on by mail. Okay, I got your
Great.
email.
Looking forward to it.
I want you to see them. He did a whole bunch of here.
Here. Everyone can hear me without a mic in here, right?
Yeah.
Yeah.
So everyone can hear.
I know. When we have the presentation here, we'll hook them in. That way, even though it's not what we want, we achieve the goal of both the online folks and the that way we can hear you, they can hear you. I think that's what we'll do. Yeah, in fact they can. So here's what we'll do. We will change the speaker. Oh, okay. It's disconnected. All right. Hey, yes, I picked up a ruler and a card. All right, go ahead and connect. I am.
I can hear from here.
You are.
Can?
Yeah.
Yep.
Can you increase the volume?
Again.
Can you increase the volume on your laptop?
Oh. It is. It's all the way up. All right, we need to see if, are they seeing me? Are they seeing my screen is all? Share.
Okay.
Okay.
We are seeing your screen.
All right, good. Good.
I'm gonna mute this. So let's go ahead and have. This is pretty loud. Is that your mic?
But my mic is on too. Did I take mine off?
No, I should take mine. Just mute it. So we wanted to have David do something. Do you want to go have David do his quick intro and then go to the speaker who's been waiting patiently to give his talk? Oh, I found some shit.
I do it on this one?
I know your card.
Okay, I'm here and ready.
Let's go, David. Let's get that done. And
Share.
Yeah.
go ahead and unshare for now.
Hit stop. Is that what it is?
Yep, that's all.
Okay, thank you.
Go ahead, David.
I
We can
wonder
hear
if
you.
any of you are familiar with the Open Star Cluster NGC 6709. It is a fairly loose cluster. It is an aquila. And the reason it is my favorite cluster is that I discovered my first comet right near there. And the poem is from Shakespeare, and it's a slightly rewritten version of the end of Julius Caesar. This was the noblest star cluster of them all. All the star clusters, save only he, did what they did in envy of this great cluster. It only in a general, honest thought and common good to all made one of them. Its life is gentle, and the elements so mixed in him that nature might stand up and say to all the world, this is a star cluster. Thank you very much. Back to the meeting.
All right, thank you, David. All right, so let's start with our short presentation now. I'm going to have Dale Parton introduce our speaker.
Hello, everyone. John Dumar graduated from Concordia College in Nebraska. Something brought him to Michigan then, teaching. He's been teaching at Lutheran High North High School for 40 years. He has taught physics and mathematics. He also, along the way, earned a master's degree in science education at Wayne State University in 1996. And he coached wrestling for 24 years. And now he is a professional archer. Quite a varied background, I have to say. And in 2015, he began his journey as an amateur astronomer. His topic tonight is measuring the mass of Jupiter, an investigation of uncertainty.
Thank you. All right, we'll do that.
They can hear us online.
Yeah, they can.
Okay. Can you see my thing online?
Yes.
Okay, very good. Anytime you measure something, there's always uncertainty. So I thought we'd start with a little activity. So you got maybe a ruler and a card. And what I would like you to do is measure across the card. Kind of like that. In centimeters. Best you can.
All right. We have a measure.
You got one? Okay, all right. So what did you get for the card? Did you get I measured it too. Did you get more than 6.29 centimeters? How many? 6.3? Anybody get lower than 6.29? Some of you? Right at 6.29?
No.
Something way different than 6.29 centimeters? Some outliers.
625.
All right. So there's always uncertainty in measurements. So how do you record the measurements? You're either gonna measure, you're gonna write down the average or the median, and then if you have, say, a caliper, you can even get another digit, but that last digit is going to be uncertain. All right. So we're going to write down the average and then some way to record what that variability is. Okay. The uncertainty in that measurement. So even in astronomy, we have that uncertainty. And Tycho Brahe, an astronomer late 1600 or late 16th century, had no telescope, but he built great big devices to measure angles. To give an idea how small of a number that he could measure, if you look at the moon, it's a half of a degree, 30 arc seconds. Look at Jupiter when it's furthest away, it's about 30, or I'm sorry, arc minutes. If you look at Jupiter, it's 30 arc seconds as we view it. So he was capable of measuring down to about 30 arc seconds. Quite the achievement. And Johannes Kepler worked for him for a year since, well, Brahe died. And so he used that data. To we can't see the whole thing. Somehow it's changing here on me. Well, we'll use it as it is. So he uses his data that Tycho collected, and in the column on the left there, Saturn, Jupiter, Mars, Earth, Venus, and Mercury. The middle column is how far away those planets are from the sun relative to the Earth distance from the sun. He didn't have absolute distances, not yet. And so Earth is 1,000. Saturn is 9,510. These are very, very good numbers. They agree very well with what we have, and so it's quite an accomplishment. And so using these numbers, and you can't see the other panels for some reason, there's the times of the orbits, how long those orbits are. Okay, and so I had a lab where I had my kids try to do some imaging of the system to get, to verify Kepler's third law of motion. And so I had a privilege using two telescopes. I had the Nexstar 130 SLT and the Nexstar 8 SE, which I got really enthused about doing this stuff, so I bought a telescope. And I bought 3 cameras. I really got excited. And so the cameras are quite different. The resolution is different. A higher resolution is going to give you a smaller number, a smaller measurement, and the larger or the longer focal length is going to give you a larger image, so you get a more precise value as well. So the combination of the telescope and the camera gives you as big of an image, as small of a precision as you can. And so here's showing the differences between the two telescopes. The line on the top is from the Nexstar SL1 of the 130 SLT, and the Nexstar 8 SE is on the bottom row there. See the difference in the size of the image, and the plus or minus how many kilometers. Each of them is plus or minus 1 pixel on the screen, but they refer to different distances. And so you can see that in the upper right-hand corner or the upper left-hand corner, 25 pixels, it refers to about 5,700 plus or minus kilometers, whereas in the bottom right-hand corner, with the more high-resolution camera and the Nexstar 8 SE, a factor of 10 times smaller. So the precision is a factor of 10. So, and that's important to get nice, precise values and low error and such. So uncertainty on the precision of the instrument's important, but so are other factors. There's atmospheric turbulence, which moves things, you know, it jostles the image. You can see it shake a little bit. So the planets and the moons quite aren't where they're supposed to be, if you like. Atmospheric refraction plays a role, the wind. So you want to image on a nice steady day. Target should be high in the sky, and don't image on a windy day or get covered. And fortunately, in 2017, when I did all this work, we had nice, calm nights. It's wonderful. It's wonderful. So here's a typical image, and Ganymede is far on the left, and Europa far on the right. And in simple software, as much as I'll paint, you can get the pixel values of the centers of the moons, and the I use the north and south pole to get the horizontal component of the position from Jupiter's center. And so I had 175 of these images and collecting all the data from the moons, and you get a graph. And it looks like this is for Callisto. It looks like all the data points are on the curve. If you have a good model, it should look like it is. But zooming in, you see that there's small variations. You got to have these small variations, otherwise maybe you're fudging the data, and because you can't get perfect data, you just can't. There's always uncertainty. Okay, and so the error bars you can't see on the normal graph. What's going on? Is this from here? No.
I would say declining line.
I don't know if I can hit that. Where's that at? I don't know where that's at.
Who's Stephen Bannon?
Probably watching this presentation.
Tell him to get off.
I would say
Steve Tendenberg, maybe you need to maybe approve or decline.
So he's asking you to.
He's asking me to.
Tab and enter.
I'm not sure what I did. You want me to just log off and log back in?
I don't know. I don't know.
Yeah, where's it?
Yeah.
Put decline.
I don't see decline on mine. Is that me?
There you go. There you go.
Oh, is that mine?
Yeah.
Oh, I couldn't see it. I'm sorry.
Just move the mouse over. You're good, Steve.
Steve, you can stay.
Yeah, I think I just figured out what I did and I declined it.
Awesome.
All right.
Sorry.
Mission decline. That's what the ATM usually says to me. I get mad.
Resume slideshow. Here we go.
Yeah.
All right. Okay. Must be this one here.
Are you able to move to the next slide?
I can't move to the next slide. There we go. I'm here. Are we stuck somewhere?
Move the mouse into that screen.
Interesting. Very strange. Should I unshare and share again?
Try that. The other thing would be to mouse over and click. Right.
The arrow. Do the arrow. Yeah, there was the bottom right. Can you pick the right arrow? Right arrow.
I think they're trying it. No. Steve's all your fault. You wanted.
All right, I'm gonna.
No, you're fine, Steve. You're fine.
Just kidding.
You're fine.
We're absolutely kidding. So here's your PowerPoint. Okay.
All right. Okay.
Now you're back.
All right. Now I'm back. All right.
We got it.
Okay. So the error bars you can't see on the normal graph, they're very small, and but on the zoom you can see those there. All right. So once you have the graph, you can glean from that the period and the semi-major axis And then using Kepler's third law of motion, and of course Newton gives us the explanation why that Kepler's law actually works with this Newton's law of gravity. And then and that was published in about 1687. 100 years later is when Henry Cavendish gets the value of G. Now we can get the mass of things. And so T squared, the period, that has error. You double that because it's squared. The semi-major axis has error. You triple that because it's cubed. The gravitational constant has error. And you add all those together, and that's going to be your error for the mass of Jupiter. Okay. So the mass will have error because all the other things have error. And so if you have a nice, real good model, here's the kind of things that you can get. On the right-hand side of the most right-hand column is from the next image 10 camera, the higher resolution camera, and the kind of percent error that can be attained, or at least that, that's what I did anyway. And the average mass I got was 1.899 10 to the 27 kilograms with only plus or minus 0.49% error, which I think is pretty good. The accepted mass of Jupiter from the Jet Propulsion Lab and from the IAU, they agreed fairly well. And of course, the JPL percent error is quite small compared to an amateur astronomer like me, but feel pretty good about that. And that was my fun.
We call it simple instruments, but good precision, and it sounds like
pretty good.
It sounds like you had pretty good, calm,
very calm nights.
Very calm nights.
Yeah.
Do you remember how the seeing and the transparency was?
A lot of the images were kind of fuzzy because there was fog a little bit, but if I can see Jupiter, I could image it. If I could see the moons, I took an image. Yeah, even though it was kind of hazy, or whatever, I still took an image. And it works out well.
How about changing the mass of the object naturally? Because Jupiter is very gaseous. I'm sure that it doesn't maintain the same mass all the time.
No, I'm sure, yeah. Or it gathers stuff in it.
Maybe you could detect some sudden change in mass, maybe.
Oh, like a comet.
Yeah, the comet. Like,
and it's going to be very small compared to the actual mass of Jupiter. Yeah.
Who knows if it's absorbed a few more times.
Yeah, it's going to be kind of small compared to the actual mass of Jupiter.
Yeah, well, of course.
Yeah. And this mass also includes the mass of the moons.
Oh, really?
It does, because the mass of moons is smaller than the precision of the mass of Jupiter that you get.
9.
Yeah, I need 2 more digits to worry about the mass of the moon.
Yeah, I was just gonna ask, if
Yeah.
you know the mass of Jupiter, could you get the mass of the moon? I guess this includes the mass of the moon. You know the period of a moon, you know the mass of Jupiter.
You'd have to actually get the mass of, like,
You probably can't do it.
I'm trying to think of, I was trying to think about how you do. You get the period of the Earth around the sun.
Okay.
Right.
Okay, and then you get the mass of Jupiter, the mass of the Jupiter plus the moons. So the whole Jupiter system, the whole Jovian system goes around the sun.
Right.
So now you have the mass of the moons and Jupiter together. Okay, and then from there, I was trying to think about how you.
I don't know.
Actually, it doesn't go
But-
around the sun.
Yeah. But getting that, it's the whole system that you get the mass of. It's like 1.89858.
If you want to know the mass of Gamma, I mean,
You gotta orbit it.
Yeah.
What is I can't imagine that the mass of even all the moons is a percent of Jupiter's mass, probably 1/10 of a percent.
It's 1 more digit.
Yeah.
It's another factor of 10. Yeah. Otherwise, I'd be really happy if I could get another digit.
So we're discussing mass, but I guess for some strange reason, I was thinking of the fact that supposedly, if there's a big enough body of water, Saturn would float. Mass versus density.
Legal ring.
Yeah, that's right. One, Jupiter's density, is it anywhere close to that? And I guess mass versus density, how does that, I guess weight wise, how we call something weight, or like how heavy it is.
Yeah, it's all just about mass. Yeah.
I don't think our online audience can hear these comments.
Can you all hear me in the online audience? No.
No.
No, they can't. Yeah, they got
Oh,
it.
yes, yes, we can. I can.
Okay, good. Okay.
There you go, Dale.
Question.
Are you talking mass or are you talking volume?
Mass.
So how do you get mass from?
From the
You're measuring the diameter.
oh the semi major axis of the orbits of the moons, and then you get period of the moon, and then that's just a simple calculation from Kepler's third law, and that's how you get the mass. So you solve for mass, knowing the period, the semi major axis is A. G is the gravitational constant that Cavendish gets, and Newton has in his equation, but Cavendish gets it.
So if you
Huh?
have no satellites,
He didn't get it. I'm sorry?
So if there are no satellites, you could not determine mass.
Right, not with Kepler's third law anyway, yeah.
Repeat the question.
The question was, can you get the mass without knowing the period and the semi-major axis? I don't think you can. You're gonna have that. Now we know the mass of Venus, I guess, and we don't, but we have orbitals. We would send probes. Send probes. No, you don't have a moon. Yeah. Don't have a moon. So Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, but not Mercury and not Venus.
Our artificial satellite.
We can use those. Yeah. Yeah, we can use those. They work. Yeah. Yeah. So we can send a probe. We have.
We've sent the probe.
Yeah. Yeah.
We're sending another one to Uranus here.
Oh yeah.
Soon, right? Or it's in the
Soon-ish. Uranus. Yeah. There was another question over here.
I guess there's no way of determining the mass of a satellite. If you have a planet without Venus, no satellite.
We'd have to send them.
But even
we send a
if
man-made satellite.
we had a satellite in orbit, you just want to, what is the mass of that satellite? I don't think you could do it. Even though you know the rotation, you know the mass of
Unless we built it.
Well, if you build
drop
it,
out.
but if you build it, you measure it before you
Right.
blast it in orbit. So
Right.
you are-
Right.
I'm talking physics here.
Right. Yeah. A natural satellite.
Yeah, without that,
We need that. Yeah. Yeah.
So you
That's how we kind of know massive stars too. Orbit stars over orbit. Stars orbit other stars.
So was there an assumption made as to what?
In the equation, no. The question is there an assumption that what the moons are made out of?
You're
No.
assuming the mass.
Yeah, no. Mass is mass. In here, mass is just mass. Yeah.
right,
It's not what it's made out of.
yeah, I guess you derive that from all of those other factors, so you don't have to actually pick it up. You use all the other factors, period of orbit, semi-major axis, and universal gravitation constant.
Yeah, it's not necessarily that it's water or anything. It's just mass.
Yeah. Because we've sent probes, we know what some of these things are made of.
Right. Or by spectra.
Yeah, by spectrum.
Right.
Otherwise.
Any other questions? Let's thank our speaker again.
Oh, thank you.
Ask the question, so is the mass of Jupiter greater, or maybe it was a comment, the mass of Jupiter is greater than the mass of all other planets in our solar system combined?
I think it is.
Yes.
Yeah.
The answer is yes, Steve.
Yeah.
Truly amazing.
And we heard loud and clear.
Good.
All righty.
I'm gonna stop this.
Well,
Thank you, John.
Yep.
all right, now I guess.
If you can bring the ruler and the car back later. to the table? Thanks.
I thought I could keep it. I need this for my bowling league. I'm the sports official. That's where at your school. That's
More minutes? 5 minutes and then our main speaker will give his presentation.
Hang on for a little bit more, Robert. We'll get you on there.
So I have a question for everybody online here. Would anybody be terribly upset if we switched from WebEx to Zoom?
No difference to me.
I'd be fine with it.
I would be fine with it as well. The majority
it
of
works
meetup groups
okay.
use Zoom, so.
As long as it works okay with the number of people.
Yeah, we've had some of our lecturers say that WebEx was a problem for them or they're uncomfortable with it, and Zoom just seems to be more common all around. Oh, one second, I did chat here. Bob's saying something. Chat. Oh God! For the first time it's your first meeting, Caitlin, I am terribly sorry about all the technical problems we're experiencing.
I'd love to know what makes it work and what doesn't.
Well, I have a feeling there's a problem with the lectern here. The HDMI cable wasn't working right. They were actually digging down into the cabling of the lectern. Mute.
I don't have the video on. Is that okay? Can you put that on?
It's Eddie Allen.
You should shoot.
He lives down.
All right.
Okay.
New PC. We're good.
And you have someone. That's it.
I will. He's still married and single, you know, he lost his sister.
We've got a couple.
Robert, would you like to try sharing your first slide just to make sure this is going to work?
How many astronomers does it take to do a hybrid meeting? 47. That's how many.
Billions and billions.
There may or may not be something in this cup right now. Well, there is. There's Coca-Cola. I wish it was something else. I've needed it tonight for all the issues.
Wait to see if Robert can share his screen.
He's trying. He can do it while we're talking.
I'm already trying to share my screen. I don't know. Oh yeah, I have to share it. Okay, so I don't know how to do that. Let's see.
So there should be a share button at the bottom.
I got it. Here we go.
Yep, there we go.
Let me try a video.
Oh, Robert, I've tried to send you some stuff. It has never worked for Astronomy Picture of the Day. Should I keep sending just in case?
Yeah, keep sending. Let me see if I can find a video though first.
Okay, yeah, go for it. I sent one that you at least. He can do it while I talk. He's just got to see if the video will work. Yeah, there doesn't require silence. It looks like it's going. Now we need to see if we can hear it. So now I'll go silent.
Hear it?
I am not hearing the audio.
Dinner with Dennis King.
There's no sound in space.
That's true, but if there's sound in your video, we should probably be here. So there may be an option to make sure you click so that it'll share audio as well.
Okay,
Let me.
if I do that, then I can't talk over my slides another way. So I'd have to especially.
Yeah, because it says share computer audio when you go to share. So if you do that, the sound from your video should come through as well. We can test that right now if you want.
Yeah, let me try that. Hold on.
I don't think you're gonna do it.
There was something.
It was audio that was a issue. So he's going to try it. And then you can look for the checkbox. Yeah, see, there it is. Now let's see if it works. Yes, it's working.
As an essential element. Can you hear me?
There we go.
Yes.
So now, okay.
Can we change the
Why do we
I'm
want
not
to?
sure whether I should.
presentation was too small.
That's his presentation. I don't think we should touch it at this point. We run the risk of
Let me try it again, but this time I'm going to play just a slide and see if I can talk over it with my voice.
Let's do it. Yeah, it's.
Yeah, it's in there. Yeah.
Yep. Select audio. We should be able to hear you as it's going. We'll find out.
Okay. Oops, that's the whole screen. I'm trying.
Oh.
Okay, so let's share.
And I just happened to look at the map.
Okay, can you hear me?
I can hear you.
Okay, good. Let me try the next slide. Can you see the slide?
Yep, I can see it. It actually came in good, pretty quick.
Okay, I think we're good.
Were you going to play the video and see if you could talk over that?
Okay, all right. Sure.
One last check. Dr. Dale is chomping at the bit to get the show back on the road. All right. Go ahead and play.
So you should hear Carl Sagan, but you should also be able to hear me.
I can hear both.
You can hear both Carl.
Sagan's a little soft, but we can hear him.
You can hear me.
And I can hear you. So yep, that is working.
All right.
All right, so you should be good to go. Once we pipe everything down, we should hear you just fine in the room. It'll be a little soft. Just talk though. Talk is normal, and we'll just go from there.
Okay, excellent.
All righty. And we can see you on our big screen up here. So, all right, Dr. Dale, I'll help you out. All right, everybody, we're about to start our main presentation. So please find your seats. The audio is not going to be as bright or as loud, but we should all be able to hear. And with that, told you.
Thank you. If you have trouble hearing, you can move forward. Okay. Well, it's been a little bit hair raising this evening for those that still have hair. Getting this show on the road, so to speak. I understand there's an HDMI cable that didn't work and such problems. Our speaker this evening is Dr. Robert Nemiroff. I'm extremely privileged to introduce him. I have benefited time after time after time from the website he manages. Dr. Nemiroff received his doctorate from the University of Pennsylvania in astronomy and astrophysics in 1987. I think he knows some things about astronomy. He's now professor of physics at Michigan Technological University. He's an active researcher with interests that include gamma ray bursts, gravitational lensing, and cosmology, and is the co-founder and co-editor of Astronomy Picture of the Day, which is, how many people here in the audience? A whole bunch of people are familiar with that website. I even use it when I'm teaching astronomy at Macomb Community College, just to get students enthused about astronomy. That website, Astronomy Picture of the Day, receives over 1 million hits every day. He plans to quiz us a little using his upcoming book, Faster Than Light, How Your Shadow Can Do It, But You Can't. Sounds interesting. And then he will give us a presentation with some of the best pictures over the last year or so from his website. So, Dr. Nemiroff, it's all yours. You've got a lot of enthusiastic people here.
Okay, thank you. Thank you. It's quite an honor. I'll try to share the correct screen, which I've already shared the wrong one once. Here we go. Okay, so you should see a slide that has a NASA logo on the upper left and a warning. Okay, good. So we'll be getting to NASA's best images. So my name is Robert Nemiroff, and so I'm from the other side of Michigan in both ways, and we're on the west side and we're on the north side of the Upper Peninsula. And so we got snow this morning, and but we had 70 degrees about a week before that. Joey Bonnell is my compatriot in creating and running the Astronomy Picture of the Day. But first, as a true teacher, I will quiz you. So please take a moment to ponder these questions. You'll be asked to consider if any of the things that I will be talking about can move faster than light. So these questions are based on a book that I am just completing, and it will be out this summer. I hope it seems to be on track. And if anyone wants a free chapter, I can actually put one right in the chat. Okay. In the book, a cartoon character named Shruggy ponders many things. So Shruggy will be seen occasionally here, and we'll be shrugging at things. Okay, so this is actually the cover for the book. It's a lot of words, you can't read it all. But Spino Hassenfelder said it's better than a new particle collider, which is a bit of a joke. But anyway, okay, so first of all, I'm not sure how I can see, I don't have the chat on right here. So let me see if people can, see if I can find chat here. No, I can't. All right, so the big first question is, can you, meaning you, if you can hear my voice, move faster than light? So there's three possibilities. One is A is yes, B is no, C is maybe so. And if I could have the chat, maybe I'll stop it and try to open chat for a second here. I'm stopping. I'm going to try to open chat. This says close chat. That means chat must be somewhere.
How many people here would say A?
Okay.
The choices went away, I guess.
So
Yes, no, maybe.
I opened up chat.
Say no.
How many
And
people
it
say
disappeared again, so I can't see. So,
how many people say you
someone said no. Okay. So
Taking a poll here in the room.
Yeah,
You might be able to see our hands raised.
some people might be embarrassed. Some people are not fast thinkers. I'm a really slow thinker, so I wouldn't be able to get these right away, or even some of them takes me a long, long time. So anyway, the correct answer to this is no. You cannot move faster than light. I'm really, really sorry. And you will not be learning how to move faster than light during this short part of this presentation.
Oh,
so that's what you're hoping. I'm really sorry. It's a bust right from the start. So we will be going to the next slide, though. It tells the answer. No, according to Einstein's special relativity, the fastest you can go is near c. C is the speed of light. Okay, so can shadows move faster than light? So this is your shadow. So if you read the subtitle to the talk, you might have an opinion here, but if you haven't, you might not. So the two possibilities are A, yes, and B, no. And if you have the possibility of chatting it, I can see it shoot up momentarily.
All right, how many think yes?
Okay, so a bunch of the chat people are saying B, no.
No.
So we might be divided.
I think we had more yeses and nos.
we had a majority of yes votes in the auditorium.
Okay, all right, thank you. And the answer is yes. So an example is to shine a flashlight at the moon and then move your hand in front at the normal speed. The shadow of your hand will move across the moon superluminally, but it's too dim to see. So if you shine your flashlight at the moon, you're not going to, even if the moon's like fully eclipsed or a new moon, you're not going to see it. But in theory, if you had a big enough and sensitive enough and fast enough integrating telescope, you could see the shadow of your hand move across the moon. The further away the shadow is, the faster, when you move your hand across, the faster that shadow can move. It's just a linear progression. The further away it is, well, it takes a while for the light to get to that thing. It takes a second and a half maybe to get to the moon. But once the light is there, the shadow can move as fast as it wants. But it's okay. So can shadows transfer information faster than light? So let's say you wanted to communicate to the moon faster than light or something, and you want to use shadows. Can you do it? A is yes and B is no.
Wow. I would say yes.
The other way.
I would say no.
I would say no.
Wow. We have no yeses and a few nos.
Okay, good, good. The important thing is to think about it. So this is a tough one. They're getting tougher. So the answer is no. There's no way that anyone has figured out to transfer locally created information faster than light using shadows. And so we're going to talk about that a little bit more later. So your shadow might cross the moon, but it's not communicating light information from one part of the moon to the other part of the moon faster than light. The information it might be communicating is from you to the moon, but that goes at the speed of light and not faster than light. So you're shrugging, he's still thinking about it. All right. Okay, what about laser spots? So teachers have laser spots. They're lots of fun. Cats love them. My cat kind of likes it. Jumps up on the wall. Can you move a laser spot faster than light?
Yes.
You can,
yes, and or B, no.
I'm gonna say no.
I say yes.
We got about half yes and half no here.
But good, that means it was actually a well-posed question. So, which means you should definitely buy the book when it comes out. But the answer is, except I told you just now, the answer is yes. So you can shine your laser at a big dome 1 light year away, then sweep your laser from horizon to horizon in 1 second. After a year, because that's how long it takes for the laser light to reach the dome, the laser spot will move all the way across the dome from one side to the other in 1 second, because that's how long it took for you to turn your laser. The only way this can happen is if the spot moved faster than light. Ooh, am I going in a wrong direction here? Well, let's go to the next question. Okay, so the speed could be considered the orchestrated, this is tortured wording here, I worked really hard on this wording. The orchestrated superposition of unrelated photons, but it is still superluminal. So you can think about those.
Wow. What does superluminal mean?
Okay, superluminal means, super means faster in a way or greater, and luminal means light. So superluminal means faster than light. Good question. Okay, now that laser spot that was on that dome, can that laser spot transfer information faster than light? So right now we're all shruggy, if you can see my pointer here.
No. We're getting a lot of answers no.
Okay, good. And the answer is no. So photons, again, they move out from your laser at the speed of light only. So the spot on the dome that was 1 light year away, you're not communicating from one part of the dome to the other. You're only communicating from the laser to the dome. And that is done through photons, and photons move at light. So you cannot transfer laser using laser spots faster than light. Okay, so what about protons? Can protons move through water faster than light?
This is yes, this is no.
Photons?
No. Yes or no?
I guess yes.
I got a lot of no.
Okay. Okay, we have a chat no. And I will say yes, sorry. So this considers, though, that the speed of light through water is given by, so I'm talking about protons can move faster than light can through water. But protons cannot move faster than light can through vacuum. But the speed of light in vacuum is the fastest that anything can go. When you shine light into water, its both group and phase velocity is much less than the speed of light in vacuum. But if you send your proton in there, your proton can actually start off going very close to the speed of light in vacuum if that's what it started at. It only slows more gradually. Therefore, if you had a race in a swimming pool between a highly energetic proton and an optical photon, the proton would win. And it creates something called Cherenkov radiation. Okay, getting near the end of these. Can distant galaxies move away from you faster than light?
Yes, no.
Yes, no.
Okay,
Yes.
I got many yes votes.
But an expert no.
But one no.
Okay. Okay. Good. So the answer is you're correct. It is yes. There are galaxies in the universe that you can see that are actually speeding away, FTO, which means faster than light in the biz, if you know, now. So if you ever shine a laser at any galaxy with a redshift Z greater than 3, that light will never reach that galaxy because the universe continues to expand as it does now. And the most distant galaxies are moving away from us faster than light. We only see them as they were in their past when they were not moving away from us faster than light. And this is because general relativity is more general than special relativity. But even in general relativity, you cannot be passed. Nothing can pass you by moving faster than light. But when you look at things far away, you get time dilation effects and space dilation effects. And given those, things can move faster than light in general relativity. And that's not controversial. Einstein would have told you the same thing. Okay, scissors. Let's say you have a big pair of scissors because it works better there. Can you close scissors faster than light? So we're all shruggy right now.
No.
No, because dealing with math.
Mostly no, but one yes.
Okay.
Two yeses.
Okay, drum roll, please. Yes, most scissors, no, but some scissors, yes. Now let's go back for a second. So the kind of scissors that you can do it is something called a guillotine scissors, where it comes down, and there's the whole thing falls at the same speed or accelerating. And if you can think about it, if you have a guillotine, let's go ahead and put this in front of me. Now it just causes me to disappear. If you have a guillotine where two things are in front of each other and they fall down, then the left part and the right part pass each other at the same time. But if you make a tiny little angle, then the left part and the right part can pass each other arbitrarily close together in time, which means the vertex in the middle can zip across faster than light. But it's not anything mass, it's an abstract thing. The vertex of the scissors, and hence it can actually close faster than light. So the scissors itself, the blades of the scissors can't do it, but the hypothetical vertex point can move across arbitrarily fast. So I actually wrote a paper on this because it was somewhat controversial, and it was accepted. It's published in the European Journal of Physics. All right, so when you turn on a room light, does the dividing line between dark and light on the walls, does that move faster than light? So yes or no, up or down.
I say
We got some yes and some no, and a lot of people not committing themselves.
All right, good. That's what I would not commit myself. Yeah. So this one surprised me. The answer is yes. It actually can. It's again abstract. The dividing line is just where the photons hit the wall. And the photons can hit the wall at different spots. It is not a photon moving faster than light. It's something that's abstract, that's moving faster than light. And again, it does not move, it does not carry information. That information originates at the light source. But whenever you go into a room and turn on a light, the dividing line between light and dark, originally the room is all dark. And then in a few seconds at least, the room's all lit up. And the dividing line was just too fast for you to see, but the dividing line between dark and light moved faster than light. And I had a paper proving that too. This is kind of a hobby of mine. Wow. Okay, so this leads to a fun cascade of superlatives. All illumination fronts across all objects are always superluminal. It's just that you can't see it because your eye and your brain work at about 1/10 of a second. And these in any room you would go to and look at, things would happen on the nanosecond time scale, so you just can't see it. So it's described in my book. Okay, is anything involving superluminal motion practically useful? Or are we just playing games here? Is this fun and games, or is there some possibility of it being useful?
I'm getting mostly don't knows, but a few are voting no.
Okay. All right. And drum roll, please. Yes. One example is because it can give you 3D information. If you sweep an approaching jet with a laser at the right speed, a superluminal illumination front will cross the entire flat wing to light up to once, which can allow you to identify the type of jet. So, for instance, just like shadows can move across the room, you can make a laser spot move across the room. But what's in the room, you can see if you can resolve the illumination fronts down to the nanosecond time scale, you can see how those illumination fronts move on the objects, and that is always faster than light, but how much faster than light tells you the increasing depth of the object. So superluminal imaging gives you 3D imaging, so you know where things are. However, if you just look at a flat photograph, like you're looking at me now, it's only two-dimensional. So the problem is that we have to do much faster. But fortunately, our smartphones, some of them have LiDAR, which is a version of this that can almost do that. So yeah, I'm considering 3D imaging to be practically useful. It's just too hard to do cheaply just now. Okay, so I think this gets harder. Let's see. Yeah, we're going to skip these and go right to the astronomy presentation now. So if you want to know these, you can ask me, or so I'm going to skip this too. So here's some publications I did, and then I'm going to get on to the astronomy stuff, which I think people want to hear more. Okay, so first of all, so let's the next part of the presentation, the longer part, go until I guess the power goes out. Which in these winds it could be any time. So what is the apod? So I'll call it apod. It's the astronomy picture of the day. So you can find it if you don't know about it. Some people did know about it, I understand from before, at apod.nasa.gov. So it started in, my colleague and I started it at NASA in 1995. And it is currently one of NASA's most popular websites. And we get, as advertised, over 1 million page views per day. We're on almost all social media. We have a Twitter, we're on Facebook, Instagram. So many of those have lots of viewers. Oops. Someone is requesting to, I don't know what that is. Okay. So I don't know if you saw that. I got a little window popped up. So let's see. So apod is translated into 20 languages by volunteers every day. So far as our log files say, pretty much every university we can find accesses apod every day. We're on a lot of social media sites. And this past year, we had a good year in terms of, well, we went for many years even without funding at NASA. So it took 15 years or so for NASA to give us a regular funding line. But in 2022, thanks in part, I think, to someone who encouraged us from your organization, perhaps the president, apod received the inaugural outreach award at the 2022 meeting of the International Astronomical Union. So here's me, I'm there 3 times. There's me, and there's Jerry. And so this is the stage at IAU in South Korea in August, where we had a great time and we caught COVID, but that's another story. Closer to home, I didn't know this until my sister texted me that apod was featured on Jeopardy on November 4, 2022. And here was the question: if you were the right person, you might have won $1,600 if you could identify NASA's astronomy picture today revealed that this largest moon of Mars may eventually disintegrate. It's scary indeed. So I'll let you chat the answer to that. And so let's go through the year now. So let's first talk about, we're going to go back to go through 2022 and 2023 so far, a lot of the science highlights and a lot of the visual highlights you could go outside and see in dark skies, which is actually a bit easier where I am up in the UP than you are down there near Detroit. But you don't have to go that far to get relatively dark skies, even down near Detroit. So early in 2022, there was Comet Leonard. Comet Leonard had a long tail that was kind of raggedy. And here was a great image that we ran on January 3rd, 2022. It was taken by the person, Jan Hottenbach, that was sent in to us. And you could not see this if you went outside. So your eyes aren't good enough. Even if you had a big telescope, you couldn't see it, because if you had a big telescope, you could only see the head and the coma of the comet. But if you had a long duration camera exposure and you had dark skies and you could see the tail go many degrees, well over 10 degrees out into the sky, which made it a good, spectacular, in fact, camera comet. So people did difference imaging. So this is my first video. This does not have sound. So again, this appeared, you can get any of these back by going to the Astronomy Picture of the Day. They're all archived. You go back to January 10, 2022 and keep playing this until people nearby object. So this is no sound, it's 18 seconds. So I ran it. So here is the comet and differencing. You can see the tail wagging in the solar wind breeze. So the comet is moving across the solar system. The solar wind is moving out away from the sun, and the ion tail interacts with the ions in the fast-moving solar wind, and it moves it around. So just like we saw in the previous slide, it can move it around. So this is a time lapse. This is not real time. This is over hours. Okay, so that was Comet Leonard, and I'm now trying to the next one. So the galactic center was, there's a Meerkat radio array. in South Africa that is just turning in spectacular images. And so here's one that was reported on February, and it actually came in a bit before that. So here you can see the center of our galaxy in great detail from Meerkat. And this came in last year. So Sagittarius A star has the big black hole in the center of our galaxy, and there's all kinds of supernova remnants. Usually you can't see this in the optical because the optical is blocking the dust toward the galactic center will block all of this. But if you look into the infrared and if you look into the radio, you can see all of this. And here are some unusual features. There are these arcs. And these are the galactic center radio arcs here. So if you want to know more, you can go to the February 2nd, 2022 Astronomy Picture of the Day, and you can click on the links because we got lots of links and they're just for learning more. Okay, so the longest recorded prominence imaged was imaged by the Solar Orbiter, and it was in March, actually in February probably of 2022. And here you can see a tremendously large prominence rivaling the size of the sun itself. And this was found by ESA and NASA, and you have to get pretty faint because the sun's pretty bright. But this is still, if it wasn't for the sun, this would be tremendously bright. And so the sun is always throwing off, particularly now that it's so active, coronal mass ejections and eruptive filaments. And here you can see an eruptive filament that was the size of the sun. Okay, Mars. So we live in a very special era. We're in a golden age of astronomy. We're sending spacecraft, robotic spacecraft, to pretty much every planet in the solar system and Pluto, and some minor planets too, Sirius and Vesta. So this is Mars. So this was from I think the Curiosity rover, and this was taken, I think, early last year. And the question is, what is this? I'm assuming you can see my cursor arrow around the center. Yeah. Somebody say something. So this is less than the size of a penny, and it seems like it's some kind of flower, but it's not, we don't think. The best theory for what this is something called a concretion, where you have flowing water in the ancient past of Mars, and in the flowing water there would be cracks and rocks, and dense parts of the dense sediment that was in the water would start accreting into the cracks and the rocks, and eventually the rocks themselves would be maybe some kind of sandstone, and it would erode away, and the concretions would be left over, and they can have some unusual shapes. So our best bet is this is not a fossilized flower. Sure makes one think though, but it is just a concretion, but it sure is cool looking. So this was debated just in the past year, 2022. Okay, so this is star formation, the Eagle Nebula. So Hubble Space Telescope, this is a Hubble Space Telescope image. But this was actually the creation of this image, although the raw data was taken from the Hubble Space Telescope. Many amateurs now can download the data and create higher and better resolution images that show features better than the people who work for Hubble Space Telescope. And the reason isn't because they're necessarily smarter, because there's a whole, as many people know, there's a whole field out there that's gaining expertise of amateurs who are just becoming so expert in all kinds of digital astronomy processing. And so amateurs can even take images of from the Hubble Space Telescope, like the famous pillars of creation, and create even better, cleaned up and higher resolution, slightly higher resolution images than before. So what you see here are eagle eggs. There are little stars that are forming in there. There's a star inside the stuff. There's a star in there. And the stars that are outside are burning away just with their high stellar winds and their bright light. So this is star formation in the Eagle Nebula. Okay, this is a really cool image that was sent to us. This was 2021, the year before. It appeared in 2022 on apod. So this is essentially a whole year. So somebody had put a camera on top of their building, I think in the Netherlands, and it took images every 15 minutes. And so you can see this hourglass shape is night and day. The dark is just the night and the bright is the day. So you can see that during the summer hours, the rooftop camera is seeing more bright than day, more day than night. And in the winter solstice around here. It's seeing more night than day. And these bright stripes here are the moon. And then astronomy imagers know that when the sun is setting, you get something called the blue hour, where it's sort of blue, and it's a good time to do foregroundscapes. So there's a lot that can be imaged, and I thought it was really cool. You can see the whole sky for a whole year in a single image. We're getting more and more aurora. Some of you may have seen aurora over the past couple of weeks because we had a real big one recently. I just heard in the preamble to this that the sun has produced another M-class flare. Unclear whether it will be aurora visible as far south as Detroit. You'd have to go away from the city lights. So we were in
Say, Bob?
Yes.
A friend of mine that lives north of Calumet recently posted on Facebook some amazing pictures of aurora up there.
Yes, many people up here, including some students of mine, just snapped some amazing pictures of aurora. This is not one of those pictures. This was taken in, I think, Sweden. But the aurora were covering the sky just 2 weeks ago. And the sun is unusually active and showing off lots of particles that hit the Earth's magnetosphere, that funnel down the Earth's magnetic field lines and can hit as far south as Arizona within the past 2 weeks. So this image, some of the more popular apod images are aurora that look like things. So this, to me, and to many people, looked like a whale. And so when we post an image that looks like something, we just get way more hits, which in one sense, who cares how many hits you get? But in another sense, it creates interest. So people say, oh, wow, they'll send it to the friends. Look, this looks like a whale. They, oh, yes, aurora. Oh, I hear there are some of those. Maybe I want to go out and see it. Maybe I want to learn more about it. So an interesting image, even though it just looks like something common, is actually a really good hook for us. So we look for hooks like this, which is why we ran this. And it was a very popular image. Okay, this was taken from near Detroit, Michigan. This was in 2021. So there was NovaCast 2021. Maybe someone in the audience took the image. I don't know if this person is there or knows the person who did. So there are maybe once a year, every other year or so, there's a nova that becomes bright enough to just barely be seen with the unaided eye. And so this was NovaCast 2021, also called V1405. And here it is in a deeper picture that has the Lobster Claw Nebula and the Bubble Nebula. Here's the Bubble Nebula. And it shows that from Detroit, you can do some pretty spectacular things, but I think you already know that because people in the audience have already done many spectacular things. But if you're just watching this, if you're kind of new to astronomy and you just want, you can contact people in the Warren Astronomical Society, and they have star parties and things where you can go out and learn how to create images. Maybe not like this right away, but you can look through some pretty big telescopes pretty quickly. Okay, over the past year, there was a really good planet parade in April, May, June. And so this was a planet parade where the planets line up in the sky. So the planets pretty much orbit the sun in the same plane. Yeah, it's a few degrees here and there. So here in the southern hemisphere, you can tell the southern hemisphere because this is the Sydney Opera House, and Sydney is the famous opera house in Australia, which is clearly in the southern hemisphere. So above that, just as before the sun rose, you can see Jupiter, Venus, Mars, and Saturn all lined up in a row. And it isn't something you'd have to really look for, with your star chart and your planet chart. You could go out, you could find where the sun's going to rise in the east, and you could say there, 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 and there they are. And if you didn't know, you'd start asking people, what are those things in the sky? So that was pretty cool. Here's another one. This was, I think, from Italy. And here we see Mercury in Italian, Venus. You can't really see Uranus. The moon, Mars, Jupiter, Neptune, you can't really see Neptune, and Saturn. So the person put Uranus and Neptune where they would have been had you had a telescope. But even on long camera durations, you're not really going to be picking these up. But still, it's nice to know where they are. And this is a really long planet parade that really demonstrates a lot of cool stuff that you can see. So this was from Italy. So that it is from Italy, and we just saw from Australia and from Detroit, Michigan. And you can see that these things, one of the great things about astronomy is that it brings the world together. These things that are visible in the sky, you can see them yourself by going outside and going to a dark place, but people around the world can see them too. And so people share their images, And so people are sharing images of the aurora the past 2 weeks ago from, Europe, from Spain. So there's some cool stuff. So, all right, there was a talk previously on Jupiter. So here's a higher resolution image of Jupiter than you might get from the ground. This is from the Juno spacecraft that is currently orbiting Jupiter. And this might look a little unusual to you. That's because there's lots of dots on it. These dots are what Jupiter really looks like, especially when Juno swoops in and passes the most massive planet in our solar system pretty closely. So the Earth is smaller than these ovals. These ovals are big storm systems. What's really unusual is this dark spot here. So this dark spot here is a shadow of a moon. And I can tell you what moon in a second. It is Ganymede. I had to consult my notes. So yeah, so you're not really seeing half of Jupiter because Juno swoops every couple months, swoops right past Jupiter. So you're seeing only part of Jupiter, and things that are near to where Juno is swooping appear much larger. So this is a relatively small spot on Jupiter, but when you're close to it, it looks like a large spot. And it looks like there's a hole in Jupiter, which is another reason why this looks interesting. But there's no holes in Jupiter that we're aware of because they would just be filled right in by the big gaseous atmosphere of Jupiter. But there are shadows. Okay, so this is something that people can do all over the world. You can find the man in the moon. Many people have heard of the man in the moon, and almost everybody is familiar with the surface of the moon in some way. But can you really identify? Let's say you had a friend who wanted to know where the man in the moon is. So where is that? Now, different societies have different things in the moon. There's the woman in the moon, there's the rabbit in the moon. The man in the moon is sort of a Western phenomena, but still, there are men in the moon from different phenomena. First, there is a man in the moon right here, but that's not the man in the moon that everybody talks about. This is the guy who took the photograph, who just happens to be looking through a telescope, and it was posed. But the man in the moon might be considered to be this. So let me go back, off, on. So these two Maria, which are dark spaces on the moon, this is like the nose, and this could be the mouth. Some people debate it, but now you can more easily point out where the man in the moon is to friends. So this is a popular phenomenon that everybody can see, even from cities. Okay, another common thing that happens today that we get sent a lot of images is we get a foreground image many times taken during the blue hour, and then like an hour or two later, a deep image of the background. And so here you can see people, again, people like to put themselves in there, which is cool. And the foreground, which is Sahara Desert. And then you can see a deep image of the background, which has the Andromeda Galaxy, some of the oldest photons you can see with the unaided eye. And you can see a little satellite galaxy of Andromeda, and you can see a tremendous star field. And we get a lot of these images. Way back in the beginning of APOD, we would consider this to be cheating. And you'd say, oh no, if it's not one shot, then we're not going to run it. But so many astrophotographers work so hard on these now. As long as we describe in the image what's done, then we're cool with these. There are two images, there's the foreground, there's the background. They are always taken, we will generally right now only accept images taken from the same camera and the same location in the same direction. So it's just different, it's an hour or two later, and it's a much longer exposure for the background. So we are now accepting these and getting some really spectacular ones. And they're really popular. So in a way, it's not like we at APOD had a choice, because these things are all over the web. And if we don't have them, then we're just showing images that, and actually they're also educational, but are not as good as what other people are showing. And we want to show the best images and explain them. Okay, so this past year, there was a pretty active noctilucent cloud season. So these are thin clouds that are very high up. So right now, and this is Paris, France, as you might guess, this is another major landmark. Here at APOD, we try to do the most major landmarks. So there was the Sydney Opera House, there's the Eiffel Tower. Yeah, if you're a world traveler, these are somewhat cliche. But a lot of people don't have the opportunity to go and see these things. And some people don't even know really that there is an Eiffel Tower. This is a major landmark in Paris. So when we have the chance, we try to educate people on the foreground, famous things in the foreground, even if they're human-made. than in the background. But here in the background, we see noctilucent clouds. So it's night on the ground, but it's day in the air. The sunlight is reflecting off of thin ice particles high in the Earth's atmosphere and giving us these strange patterns that can change over a scale of minutes. They're not aurora. They're reflections of sunlight. They're brighter than aurora, but they're only visible while the sun is illuminating them. What causes them is actually, we know some causes, but we don't know them all. Things that can deposit ice in the upper atmosphere. It could be satellites of the plume of spaceships or comets or meteors can also create some of this, but we don't know all the causes for noctilucent clouds. Okay, this was kind of a puzzle we did, so I'll puzzle you too. See if you can find the new moon. So almost always when you see a movie or a TV show, you'd think the moon is always a full moon. And if you ever look up at the sky, you see what's wrong with the moon. It's only like a crescent or a gibbous moon. But sometimes just as interesting is a new moon. So a new moon is when there's a tiny little sliver or almost no moon at all. So see if anyone can find it. I guess you can't really chat me where it is, but you can give a thumbs up to your neighbor that you can see it. It's tough though. So give people another couple seconds. Makes this a bit interactive. So again, you can stare at it yourself on the July 25th, 2022 apod. Okay, so there's a thin sliver right here. And one of the reasons why you can't see it is because it's new, because you're just beginning, the moon was almost not there, and then you just begin to see a sliver that's going to grow into a crescent, which is going to grow into a half moon, which is going to grow into a gibbous moon, which is going to grow into a full moon, and it changes, goes through the whole cycle every month, which is also called month. Also, this is relatively low to the horizon, and so there's a lot of the air of the Earth's atmosphere causes a lot of extinction near the horizon, and it makes things that are bright appear relatively dim. And so even though if this sliver of the moon was seen up higher, then it would be more visible, but it's down near, and there's also some light from the sun still reflecting off. So there's three reasons why this is actually hard to see. But when the title of the email, I think, was Find the New Moon. So the first thing we're doing is we're looking real close to try to see if we can find it. So it's kind of fun. So we included it. I also like how simple this image is. You got the blue water, you got the orange sky. Why is this on apod? Apod's about the most spectacular images, but it's one of the more interesting images because it's a puzzle. It's simple and it's a puzzle. Okay, so we live in a time, this is another video, so apod's running more and more videos because there's more and more videos available. We're being sent more videos. This was done by NASA's Science Visualization Studio. And so what's going to happen is we're going to see the Earth's climate spiral, Earth warming from 1880 to today. I will note that the Earth is about several degrees cooler than it was a couple million years ago. But right now, in the past 150 years, it's warming. So here we go. I don't think there's any music to this either. So here we see as the months go by, the little thing goes around and around and around, and the years go up and up and up. This is going to take a minute and 10 seconds, so you don't get too impatient. So far, it doesn't look like the Earth is warming, so good for the early 1900s. But as the months go by and the spiral goes around and around, it seems to be getting a little bit out there. And this is the difference between -1 and 1 degree Celsius, which is about 3 degrees Fahrenheit or so. So now we're starting to see it get into the orange. And in just the past 150 years, the Earth is warming up. And it goes round and round. And this is data from NASA satellites and other satellites. And here we're coming on the present day. And it's warmer. And now it's going to turn on its side so you can see a visualization of the Earth's climate spiral. So this is considered by many to be one of the biggest problems facing modern humanity. So NASA and people are trying to figure out what we can, if there's anything we can do, how much the Earth is warming, how much the seas are rising, how much the seas are becoming more acidic, and what we can do about it, how humanity can adapt as best we can to this. Okay, this is back on Mars. I think it's Curiosity again. So this is an unusual feature. Curiosity is rolling around Mars. It's a robotic thing about the size of a small car with unusual wheels. And what's unusual about this is that it's got young rocks on top of old rocks. And that's why I ran this. But that's not why it was really popular. It had to be pointed out to me why this is one of the more popular images of this month of August. And the reason is because this looks like a battleship from Star Wars. And I had no idea. And anyway, it was an unusual hook, and sometimes you luck into it. But for reasons because of some upheaval on Mars that we don't know what it was, there's young rocks that are darker lying on top of older rocks, which are younger. Okay, so 2022 was the year we started hearing from the Webb Space Telescope, James Webb Space Telescope. It was launched on Christmas Day on 2021. I don't know if anybody saw that or saw the video of it, in a nail-biting launch, and then it had to unfold in many ways, and it did it, and it did it great. And so we're all happy to have a working space telescope that's several times bigger than the Hubble Space Telescope, but features on looking in the infrared. It actually goes sort of into the orange in the optical. But here we can see the Carina Nebula. It looks like cliffs, but it's just really dust, and it's seen in tremendous detail, better than it's ever been seen before by the sun orbiting. It co-orbits the sun with the Earth, James Webb Space Telescope. So we've entered a new era, and hopefully Webb Telescope will live for many years. Hubble's still up there. We're not shutting down Hubble, but now we're actually in another golden era. We're in a golden era because we're sending spacecraft all over the solar system. We're in a golden era right now because we've got two major space telescopes operating. So one thing that I didn't expect is that you can train Webb on Jupiter. I figured, well, we pretty much know everything about Jupiter, especially since Juno is there. But looking at Jupiter in the infrared actually is pretty interesting. So you can see the rings of Jupiter. So many people don't know that Jupiter has rings. You can see the Great Red Spot, which appears in this band of infrared light to be kind of white. And you can see aurora, and you can see also Io's footprint on the aurora of the southern aurora on Jupiter. So, and you can see tremendous detail in the infrared in Jupiter's clouds. And typically the lighter clouds are higher up, and the darker clouds are lower down, but it's just a spectacular image. And this image was processed in great detail by an amateur astronomer, Judy Schmidt, who has submitted many images to apod, and she's not a professional scientist, but she knows more about analyzing images, in particular Hubble and Webb images, than probably anyone alive. And so when NASA now wants an image to really bring up the different features of the image, she is one of the people they might contact, who is a graphic designer who lives in California. But she can make images pop just like she did this one. Okay, so this is an image of the Tarantula Nebula, which is in the Large Magellanic Cloud, which is a smaller satellite cloud to the Milky Way. And this is in near infrared light, and you can see all these bright stars here. But when you go to further into the mid-infrared, you see a different image, but it's both from Webb. Again, we're showing some of the great Webb images that came in. So I'm going to go to the next image, and you say, oh, this is a completely different image. But look at this star right here. I'm going to go back. This star right here. Oops, that's too far back. It's the same star. So let's look at this star over here. It's the same star. So you're seeing the same field. But what you don't see is you don't see a lot of the blue stars, the stars that you can see in the optical light so easily. So also when you go to the next one, you can see it's less resolution. So when Webb goes into the infrared light, it can see through dust better than ever before. But because red light has longer wavelengths than optical light, you lose some resolution. So, but Webb can image things in multiple bands, or from orange light into the mid-infrared. And so we can examine things like this star cluster, which almost disappears in the mid-infrared, and try to see how stars form, especially in these star clusters and in many other ways. So Webb is useful because it can see not only in high resolution, not only because it collects so much light from its huge mirrors, but it can see in different bands of light. Okay, so another thing that happened this past year is that we practiced planetary defense. NASA did in particular. So here you can see Didymos is, I think, this asteroid, which we didn't know what it looked like. And Dimorphos is the small one. And so this is a video you might be able to tell from the thing at the bottom. And so what we're going to do is we're going to spend the next 18 seconds pretending to crash into this guy right here. And so we'll do that, and then I'll talk about it a bit. So here we are. So the DART mission from NASA is moving. We didn't know what this small object looked like before, but then we got a great view of it, and then this is slowed down now. We found out that it was a rubble pile, and then DART stopped communicating. But it told us it hit the asteroid, the small asteroid, with such force that it slightly altered its orbit, which is what NASA was mostly interested in. So what we wanted to do is we wanted to prove that if we were to hit an object, an asteroid, early enough, then we knew its orbit well enough that we could alter its orbit so that if we see an asteroid that could cause problems for the Earth early enough, and we were to hit it with something, we could knock it off and then it would miss the Earth and we could protect the Earth. Now this, Dimorphos wasn't a danger to the Earth. And there are Earth-crossing asteroids that could be a danger to the Earth, but we don't know any of them that are going to hit the Earth. But it could be because there are mass extinctions that are thought to be because of asteroid impacts that could happen in the next 1,000 million years. And as we develop the capability of tracking asteroids better and of launching deep space probes earlier and being able to hit them, we are able to defend our Earth like we've never been able to in Earth's history. So one unexpected thing, let's go to the next one, is that this was taken from the ground. So here you see mostly the bigger one. And I'm going to play another video. This runs 13 seconds. But what people didn't expect is to see a great plume. I always have some audio. Actually, the audio is from a background image. So here you see a plume moving out. So this was somewhat unexpected. So the asteroid was a rubble pile, and it had a lot of very fine grit. So when it was hit by the DART mission, it made a poof. It made a bigger poof than we expected. And you can see that poof from Earth. Okay, continuing on the James Webb Space Telescope hit parade. This is the dust gels around a Wolf-Rayet star, Wolf-Rayet 140. And so Webb imaged this. And so this is a massive star that has chaotic winds that are throwing off particles much more faster and more tumultuous than the wind from our sun. But this guy has a massive companion, and they're going around each other. And every time they get close to each other, you see an X-ray event that's seen with X-ray satellites, and you see another ring that comes out. Exactly what causes the rings, we don't know, but we know they're coming because every few years, these things go in close to each other. And so Webb was able to see this in greater detail and see these rings, more rings than have ever been seen. But Webb sees such deep stuff, you can actually see galaxies around the edges. Okay, so we're getting near the end here if people are worried about the time. So one of the biggest gamma ray bursts, brightest gamma ray bursts of modern times was seen on Earth this past year. And so this was sent to me from Ann Arbor, from John Miller at University of Michigan. And so this is an X-ray part of the glow. So this huge flash in gamma radiation was not bright enough to damage life on Earth. Although we worry that millions and tens of millions, hundreds of millions of years ago, there might have been bright enough flashes from gamma ray bursts to affect life on Earth and might have even have led to some extinctions. So this is the brightest one we've seen recently, but it wasn't that bright. But what it did is had a lot of X-ray, and this X-rays bounced off of dust in planes in our galaxy and created these rings centered on this gamma ray burst. And this looks a little bit like a cartoon or an illustration, but it is not. It was taken by the Swift satellite, and the data was accumulated and smoothed over by John Miller at University of Michigan. He sent this to us, so we thought this was cool. All right, come Halloween time, this is not taken by Webb telescope. Again, a lot of our images are by amateurs. So here you can see some star formation in something that is called the Cosmic Bat Nebula. And this was the best image of the Bat Nebula I've seen. So we ran it on Halloween, although it was sent to us several months before. We just held on to it and said, oh no, I know when we're running this one. And so we did it. So it was kind of cool. Okay, so there's been lunar eclipses in past years. This lunar eclipse was captured from the South Pole. So here you can see stars in the background. You can see aurora. Those are southern lights. And the lunar eclipse is a time lapse that goes across here. Here you can see people waving like they do. A lot of the images, as you know by now, are sent with people waving, and that's cool. So this is a microwave background measurement thing, trying to measure the early parts of our universe. But what gets our attention now is this line of the moon, images of the moon consecutively. So when you're not on one of the poles of the moon, you can see the moon rise and set. But here, the moon during a month will essentially just go in a circle as the Earth spins and causes the moon just to go in a circle. And so it's interesting to think about and see. And this combined a lot of things all at once. This is taken very near the South Pole of our Earth. Okay, during the end of last year, we saw NASA launch the Artemis 1. So Artemis 1 went around the moon, the far side of the moon. There were no people involved. Although the next one, which will come up, I think next year, will involve people. And we'll again go around the far side of the moon. But here you can see the Earth and the moon together. Again, taken in a recent image from a NASA image. So the Artemis is NASA's set of missions that's going to send people back to the moon and eventually to Mars. But there are lots of other images, lots of other spacecraft. We live in another golden age. So you thought it was golden age. Maybe we should call it a platinum age, because there are private spacecraft that are now being sent to land on the moon. And one just failed to do so from Japan about a week or so ago. But there are many more attempts, several more attempts coming up in this past year. But humans will be coming back to the moon next year. This is one of these spectacular foreground background images that are sent to us. This just had too many things to ignore. Here you see the Big Dipper, where the stars, I guess, were slightly, this is from northern Norway, so you can see tremendously bright aurora. You can see them reflected. You can see a tremendously interesting foreground. You can see the Astronomy Galaxy. You can see the band of our Milky Way galaxy. Here's the star Vega. What can't you see? There's a meteor. So it all made it into here. And so here's the guy lighting the foreground, so you can see the foreground because it would be too dark otherwise. And we like these images because they teach things about the sky. They show what aurora look like in angular images compared to the rest of the sky, what a planet would look like, stars and planets and galaxies. And we're seeing a lot of these, and they're just really cool conglomerations. And again, these are all taken on the same night. There was another bright comet ZTF for Zwicky Transient Facility, and this was visible in December, January, and it had a bright green coma, and it had some ion tails that were off at different angles, and you could just barely see its coma with the unaided eye, but cameras got some pretty good images of the tail and tails. This was an interesting year because as James Webb Space Telescope and other missions see exoplanets, they see evidence of exoplanets around other planets, not the sun. They see this in any number of ways, one of which is just because it slightly eclipses the planet. So you see a slight dip in a star's light by a planet going in front of it. And so we can tell a lot about the planet from that. But what we can't do is we don't really have an image of the planet. But we know about where it is relative to that star, not our sun, and we know what type of star it is. So we're sometimes sent artist renderings, but now with Webb, we can just ask artificial intelligence to pretend what it looks like from the surface of that planet. We can give it some parameters, some prompts, and they can say, okay, look, it's probably, this planet is really close to the star. This star is kind of red, so we can put it in the sky, and there's probably lava. And so you can create something that we think is visually interesting for the viewer of APOD, instead of just, here's a here's a light curve. Here's what the planet might look like. Here's a planet, but oops. But so one of the great things with artificial intelligence is that it can create images that are, as best we can guess, correct, but they're not actual images, they're illustrations, as we say, and portray modern advances in a new light. So just recently in March, many of you might have gone out and seen at sunset, there was Jupiter and Venus right next to each other in the sky. Even if you didn't know about it, you went out, you could see these two bright things in the sunset sky. And here we see a amateur astronomer showing his, two astronomers. This one looking through a telescope, although you didn't really need a telescope because Jupiter and Venus were pretty bright, showing the kids the sky. So that's great for these bright events where you can just go out and see it and you just point in the direction. And these were just very obvious from any city, from any place in the northern hemisphere, actually even in the southern hemisphere. This one was from Germany. You can see a sky event. Okay, there's got, I think, just a couple more images. This is Terran 1 was not launched by SpaceX. SpaceX was launched by another company, and it burned something called methylox, which is, I think, let's have to go to my notes again. Let's see. Okay, it's composed of liquid methane and liquid oxygen called methylox. This is a Terran 1 launch from Cape Canaveral, not by SpaceX. There are other SpaceX is great. They're going to the space station. They're launching the largest spacecraft that we've ever attempted to launch. But methylox is interesting. Methylox is interesting because both these things are thought that it might exist on the surface of Mars. And if you can go to Mars and you can mine things that you can then put in your spacecraft and burn, that's another thing coming. So I thought this was really great. And many people did too. And just last week, there was a solar eclipse. But wasn't visible from here. It was visible from Western Australia and small islands near Western Australia. So here you can see the corona of the sun. And so this is interesting because a year from this month, a tiny, tiny bit of Michigan, I think, will be eclipsed on April 8th, 2024. But that's not where you want to see it. You want to go into Ohio and Illinois to see, not far from Detroit, drive for a couple hours to a really good spot and see the next total solar eclipse of the sun visible from the USA. And NASA and lots of organizations like the Warren Astronomical Society are ramping up to do this. So you will be able to see all of this yourself with your unaided eye, although you should probably use special glasses to see the before totality. But we are 1 year away, less than 1 year away from being within driving distance of seeing a total solar eclipse here in the USA. And with that, I will leave with a video from Carl Sagan. It's 3 minutes and 50 seconds. It talks about why we are in such a golden age, because we are wanderers. And this was put together by visuals. Many of the background visuals are real images, real NASA images. The music was imposed on it, and the foreground that you see, little spacecraft, that's all made up. And the words and voice were taken from an old video, of Carl Sagan's, and then put onto this. This was all put together by Eric Vernquist. And so here we go. And after this, I can take some questions. This is the last slide. If you can't hear it, somebody tell me. Let me turn it up.
For all its material advantages, the sedentary life has left us edgy, unfulfilled. Even after 400 generations in villages and cities, we haven't forgotten. The open road still softly calls, like a nearly forgotten song of childhood.
That's really the Earth. That's not a real spacecraft.
We invest far off places with a certain romance. The appeal, I suspect, has been meticulously crafted by natural selection as an essential element in our survival. Long summers, mild winters, rich harvests, plentiful game. None of them lasts forever. Your own life, or your band's, or even your species might be owed to a restless few, drawn by a craving they can hardly articulate or understand. Undiscovered lands and new worlds.
There is no space elevator down to Mars yet, but maybe one day.
Herman Melville in Moby Dick spoke for wanderers in all epochs and meridians. He said, I am tormented with an everlasting itch for things remote. I love to sail forbidden seas.
This whole thing doesn't exist. This is from like Grimworld. Science fiction. That's really Jupiter and I. It's Saturn. Uranus that you can actually jump off of. I agree with the solar system, but not die. It's not high enough
Maybe
gravity.
it's a little early. Maybe the time is not quite yet. But those are the worlds promising untold opportunities beckon. Silently, they orbit the sun, waiting.
Okay, so I will stop the video. I'm happy to take questions. I hope you enjoyed the presentation.
Let's thank our speaker. Any questions? Yes.
A question about speed of light and the possibility of capturing at some point the force that actually makes the universe expand faster than the speed of light. I know that mass can't go that way, obviously, but why would we not explore the possibility of finding a way to capture the expansion of the universe as a power to get us moving faster than that?
Could you hear the question?
Yes, I did. So that's a really good question. So there are people who actually are speculating on that. There's something called the Abercrombie Drive. I don't know if I'm pronouncing it correctly, but there's people are trying to study that. And the idea is you create an expanding bubble that expands superluminally, and then you jump onto the bubble, and then you jump off the bubble, and then you would have moved superluminally. But that is quite speculative, and with the technology to do that, and even the physics that goes into that, is hotly being debated, but it's a good idea, and it's an idea that people are thinking about for hundreds of years into the future. We don't know if it can really work, but it's a very intriguing idea.
Thank you.
Bob, good job.
Thank you.
Question, sir. I'm wondering what your criteria is for choosing your apod photos, because a couple good friends of mine, one whose photo you showed from here in southern Michigan, have had their photos on apod, and I'm just wondering how many people determine which picture to choose, and what your criteria is. You got to get probably thousands every day.
Well, good question. Thank you. So we get about 20 a day or so, and we're looking for. So who decides? So I decide. So I decide for half, and about half, and Jerry Bennell decides for the other half. And generally, we don't consult each other. It's single decision. Now, one thing I do is when images are submitted to me, I post, I take what I think are the best images that are the most topical because they're about something that's happening, the most educational because they demonstrate something, the most visually spectacular, and I post them. I have a student of mine post them to a Facebook page called Facebook Sky. And then what happens is we see how popular it is. Now, popularity is not the only thing that determines whether something appears on APOD, but if something is very popular, it makes it more likely that we will choose it for APOD. So if it's popular on Facebook Sky, it almost certainly will be popular on Facebook APOD, and it will most certainly be popular on the regular NASA APOD. So we post at least 2 images a day, sometimes more, on Facebook Sky, and we tell people right off that it's a that these are some of the best images, and people are actually very. We get a lot of email that they're very pleased to even have made it onto Facebook Sky. Then as I said, we judge the popularity from that. But if there's a very topical image, a launch of some sort, a meteor shower of some sort, then it doesn't necessarily, it might not even be time to put it on Facebook Sky. Some things we just know are going to be real popular anyway, or just have such great educational depth that we can't, it demonstrates something that I've never really seen demonstrated before in a very good way. And then so partly APOD's goal is education, and so we will run those images too. So if you've taken a good image, please submit it to us. We like to see lots of images because then it gives us a great selection to choose from. And then if we find it intriguing, we will put it into our focus group sort of on Facebook Sky. And if it does well there, it increases the chances that we'll run it on APOD. But then again, we're getting 20-to-1 images, right? So the raw chance of anyone sending in an image that's going to appear is 1 in 20 at the best. And it's probably lower because you know the NASA missions don't compete like that. So we see if there's an image of a new image of Pluto, you know, we don't have to run that on Facebook Sky. So so yeah, it's difficult. But one of the things that I try to picture is that if I was going to be, if there's going to be publishing an astronomy textbook, is the image that's being sent to me, is that something that might appear in that textbook? Is it so good that it's the best image of the Orion Nebula? Is it showing something of the image of Titan that hasn't been seen before? So that's going to appear in the book. If my answer to that question in my mind is yeah, that might well appear in a textbook, then that really makes it much more likely that I'm going to run it on Astronomy Picture today, because we are our name. It is the picture that is sort of in the mind of astronomers and the astronomical realm of that day. Even if it wasn't taken on that day, it is the one that would normally get the most discussion on that day.
Very good. Yeah, that's got to be a fairly unique image, obviously, but I'm really surprised you only get 20 a day.
Right. Well, and one of mine actually made it to Sky, but it didn't quite make it to APOD. So I guess that means I should keep trying.
Please keep trying. So some people think that they're somehow they failed as an astrophotographer if their image doesn't appear on APOD, but I don't think that's true at all. People are always doing their best, and the amount of amazing images we're getting submitted today is way different than we were 25 years ago, when the only amazing images we were getting submitted 25 years ago were essentially from David Malin. Okay, but now you can get the David Malin Award, but because there's so much amazing stuff you can do with digital technology and with the equipment to see deep and to take out satellite trails and fix pixels is now well known. And so the images we're getting today every year are always better than the year before. And with the new artificial intelligence, now you can just sort of tell your artificial intelligence to clean up the images and take out the satellite trails and remove this thing. And it's done much more quickly, instead of the hours of painstaking thing that many people there might know of cleaning up your image. Now you can almost wave your magic wand and get it better. So the images are getting better all the time. So please, I want people to do this for their own edification, for their own satisfaction. don't. It'd be great if you were featured, if someone was featured on APOD, but please don't make that your goal, because it puts a tremendous,
Agree.
impetus on us that we do try to run new astrophotographers as often as we can. But I think people should consider their own. So when you run in the, comes to my mind, the Boston Marathon, don't try to win the Boston Marathon. Try to get your best time. Try to have fun. Try to become someone who is always doing better than they used to impresses their family and friends. Okay, that should be your more goal. Impress your friends. Show it to the Warren Astronomical Society and other astronomical societies you're part of, and that's the real victory in my
Oh, agreed. We had a question.
How or where does one submit?
How or where does one submit a picture?
Okay, very good. So go to any NASA APOD page and look for, the phrase submissions. It's hot linked. It tells you exactly how to do it. The best way is probably to send us emails, but how do you know our email address? It's on the submissions page. So it's
I think I still have both of your emails, so
okay.
I will.
Any other question?
Thank you.
Thank you so much.
Okay. Thank you for inviting me. It's been great.
Salute.
I appreciate the invitation. Okay. So.
All right.
Okay.
Take us out.
All right. Well, our next meeting is Thursday, May 18th, in 2.5 weeks, in person at Macomb Community College, South Campus, Building E. We only have room for 35 people, and people do get there early, so get there early. Afterwards, we meet at a restaurant. Did anybody go to that Coney Island last week? Or the last meeting? Was it any good? Good. Okay, so fine. We'll keep doing that then, because we're too late to order at the other place. So the Coney Island is on Old Woodward, block south of 13, isn't it?
What's the name? It's Leo.
Leo's Coney Island.
13 in Old
Woodward.
Look for the 15.
Anyway, so we're signing off. We've got to get out of here in Cranbrook. Good night, everyone, and thanks for coming.
How many people do you have at Cranbrook tonight?
I'd say about 30.
Thanks.
All right, good night, everyone.
Night.
We gotta vacate. All right.